Hey guys, welcome back to the Transformer Slam Learn With Me series. So, in continuation to the previous episode, we will try to use whatever we have learned so far in episode 1 and 2 to create a convolution neural network in this one and test it out on some sample data set. So, what we are going to do first is to draw out a plan, maybe, mm, depending on whatever we have learned so far. So, what we need is let's go back and take reference. So we need, of course, first our imports. So first we need is our imports, then we need our data loaders, so training set and test set. So we will have data loaders. We also Okay, so here is the data sets and here is the data loader. So of course we will have data sets, data loaders, and we will be specifying the device. So device selection. Mm, we will be creating our neural network. So create network. Mm, we will have our loss functions and optimizers. Loss functions, optimizers for the backpropagation. We will have our training loop. Do we need a test loop? We need a test loop if we are iterating through our data, but if we are doing it for just one sample data, then maybe we don't need our test loop. But anyway, just for reference, we will keep train loop and maybe a test loop. And then based on epochs where the train loop is run. Okay, so I'll just do it here itself, epochs. And then we will be saving our model, loading our model. So in our data set, we need to know what outputs belong to what classes, and that is very specific to data set. So I have planned to use MNIST dataset for this one, and we'll see how that works out. But anyway, so we'll just make a note. We will be saving models, loading models, and then we'll be doing prediction, for which we will need class specification. Okay, so that's the plan. Let's try to follow it along and let's start. So first is our imports. Okay, then we have data sets. Let's check what all data sets are available. Going back to the reference documentations. So image datasets. I know about MNIST. So we're going to use the MNIST dataset and we will try to load it in the same manner. We'll see if it's the same or not, but so we have our train and test data sets. Then we going to have data loaders. Um, okay, but before that, I would also like to do this to just specify if specify the device that we're going to use. So that's that. And coming back to data loaders. So I'm going to use whatever we used in the first episode for the data loaders. So in the similar manner. So that will be our data loaders. Device selection is done, creating the network. So let's try to follow the same outline for creating the network. But of course there will be some changes to it. So here I'll do my CNN network. Okay. Okay guys, so I took some help of GPT to help me create this CNN network for me. Going back to GPT, this is what it suggests should be in the init, and we'll see what it is. So in a similar manner, first of all, we are overwriting the init of nn.module. Then here we are creating a convolution layer. Then there is max pooling layer, then another convolution layer, and then we have fully connected layer 1 and fully connected layer 2. Okay, so since convolution operations and max pooling operations are very common in uh, in creating any neural networks, very common and very basic. So PyTorch has a ready-made functions to create the objects for that, ready-made classes for that. So we have nn.conv2d to create a convolution layer, and then we have similar manner nn.maxpool2d to create a max pooling layer. Let me just quickly find out about the parameters. So guys, going through the documentation, it says that the first three are supposed to be in channels, out channels, and kernel size. We saw in the last episode what in channels and out channels are. Kernel size is the kernel for convolution. To give an idea, so suppose this is your whole image in the green. This will be your kernel, and this kernel does convolution operation. Again, I won't go into the mathematics of convolution operation. This kernel does a convolution operation on each pixel here, each pixel one by one. Okay, and the output of that convolution operation is what goes into the final output as the output of the convolution layer. Okay, so that's how, so basically what we have to define is the size of our kernel here. The documentation says that for kernel size, if you define a single value, that will be the value of height and width both. So in this case, a kernel size of 3 would mean a 3 cross 3 kernel, and a kernel size of 9 would mean a 9 cross 9 kernel. If you want not a square shaped kernel, then you can define as a tuple. That's what it's written here, in which case the first one will be height and the second one will be width. So that's how kernels are defined. So This is supposed to be in channel, out channel, and kernels. I need more explanation on that. So let's see about it. Okay, so why I was confused is that why the out channel is 8. So in channel 1 basically means that normally it's going to be a grayscale image. That's why in channel is 1. Out channel 8 means that 8 different types of features will be the output from convolution layer. So that's why the out channel is 8. And since we are defining it in this way, if you go back to the documentation, it says that the rest of the parameters have uh, some default values. That means since we are defining in this way, the rest will take just the default values. Okay, so let's go back and do the same with max pooling. Let's see what max pooling says. Okay, here again we have okay. So the kernel size is 2 in this case, and kernel shifts by 2. Max pooling, let's see max pooling. To define max pooling operation definition. Okay, so max pooling basically is downsampling our image. So basically, for example, if we, yeah, here we have the example. So suppose we have a image of like 4 cross 4, then a 2 cross 2 kernel max pooling will reduce the image to 2 cross 2 output. So basically images will be downsampled. Why max pooling is done in convolution is because, if I remember correctly, to be able to detect features on different scales, same features. So for example, if you have a dog, image of a dog, and you are trying to extract features from image of a dog, you would ideally want that no matter what size of the image is, whether be it 1080p size or 720p size or 256 cross 256 or 512 cross 512, whatever, you would ideally want that at every scale your features are detected correctly, right? So to do that, max pooling is done to keep downsampling the images and be able to detect features even on those downsampled images. So one more thing about this whole process of convolution, max pooling and convolution. If we go back to the process of convolution, so here we have our kernel, we slide it over. So for this pixel, the convolution kernel will come something like this. For this pixel, it will come something like this. Even here, this top line going here, and that's how it will keep on sliding over all of it and finding out the values of whatever output of the convolution is, and will be populating here in the output. But what I wanted to understand more is what is the meaning of having one channel for input and 8 channel for output. So what it basically means is this kernel that you see here, the value of the kernels, this will be 8 different values. So with 8 different values, the convolution output that we'll be getting will be 8 different types of convolution output. That's what I learned. So what happens is if you have one one input dimension and 8 output dimensions, that means that your image, this image, is being convoluted with 8 different kernels producing 8 different outputs, and those 8 different outputs is what you're getting, is what is the output of your convolution layer here. Okay, and then when max pooling happens on the size of the uh, the input image. So in this case image, so for example you have 16 cross 16 image, then max pooling happens, then your image reduces to 8 cross 8, right? But the channel still remains same, the 8 different outputs of 8 different convolutions. So that's what goes into the second layer of convolution, and here we are defining 16, so that means it further goes and expands into 16 different channels with the 3 cross 3 kernel. And then we have our fully connected layers. So we have already seen about fully connected layers. So that's the overall of how the CNN network is built. And for doing the forward pass, going back to the GPT, this is our forward pass function. We will see in detail how it is working. Okay guys, so I asked GPT again to explain what's happening here. So what it says is, here first of all we take our data, we apply convolution on it, and then we apply ReLU activation on it for non-linearity, and then we apply pooling function, max pooling, and then again we go for the same process again. So whatever is the output of this whole thing here, this whole thing here is taken into X, and then again for that X we apply convolution, we apply ReLU activation, and then max pooling again. So one thing to note here is we are not specifying ReLU explicitly in our model like we did in previous episodes. Like here we specified ReLU here, but here we are just calling ReLU directly in the forward pass. Why that's happening is it's always doing the same thing, applying the ReLU activation, but here since we are using NN sequential, so what sequential does is that it creates a pipeline, and however these layers are defined in the pipeline, it moves ahead in the same manner. So first this will happen, then this will happen, then this will happen. However, in this what we are doing is we are just defining our layers, and we are specifying the parameters for each of those layers, and then we are free to call it in any manner that we want for forward pass. So that's the difference between the two. So that's a nice concept to understand, which is specific to PyTorch. Okay, and then going back to this X view, I need to understand about this. So GPT tells me that what this is doing is whatever output we have here, the tensor output, it's flattening it out into single dimension. And why that is happening is we need to further pass it to the fully connected layers. We have our convolutions, but then we need to further pass it to fully connected layers 1 and 2, right? So it has to become a single dimensional vector. So that's what this is doing, and then this is being passed through the fully connected layer, and then again a ReLU activation is being applied, and then again it is being passed through a fully connected layer, the second fully connected layer, and whatever we get as output of that is what the forward pass returns. Okay, so that's what is happening in the CNN network. So moving ahead, we have our network, and then loss function again will take help of GPT. We are doing cross entropy loss, which we have seen so many times earlier as well. Cross entropy loss. Optimizer, we'll see what optimizer is suggested. Adam optimizer. So I've heard about Adam optimizer a lot lately. This is one of the go-to optimizer for many modern operations. So anyway, let's take this one. So if you compare it to our first episode, whatever we did in the first episode, we are doing the same thing. We are creating our loss function and the optimizer here, right? The loss function and the optimizer. So just to keep everything uniform, let's name it also in the same manner. Okay. Okay, and we will move ahead. We are done with loss functions and optimizers. Now we have our train loop epoch. So maybe let's define epoch to be 5. And we'll go for the train loop. So this was our train loop in the first episode. Let's try to use it and then maybe modify it as required, but the reference will still be this for better understanding. Here we have a train loop. In the previous example we did not have a train loop, but anyway, let's going ahead, let's see what they say. So comparing what GPT is suggesting to what we have, we are putting our model in train loop, okay, train mode, okay, for epochs and range epochs, for image labels and train loaders, which is batch XY in data loader. Image and labels. So this should be our image, this should be our labels. Batch. So what this is telling me is that if we do it in this way, then for each batch we will have a single image. Usually we don't want that because typically a batch consists of more than one data point. Okay, so what I will do is I will not follow what GPT is suggesting, but rather I will follow what the official tutorials suggested and what we followed in the first episode, and we'll see how it works out. Anyway, so we have our training loop and then epochs, train. So we are going to do this again according to what the official documentation had suggested. So epoch we have already set, so no need to do it here. Test, we do not have the test function yet, so I'm just gonna comment it out. I'm just gonna train it first. I'm trying to be a little, I'm just doing little experimentations of what works, what does not. Let's see. And then saving the model. So I'll do again what the official documentation had suggested, which we followed in the first episode. Saving the model and then loading the model. Okay, and then making a prediction. Okay, so making a prediction. So ideally, what we would want is to make a prediction. We will pass our data. We will pass our data to the model. Whatever logit outputs we are getting, we have to ideally run a softmax on that, get the classes, and then we print out those classes. So that's how it should ideally be. Let's see what GPT has suggested. Yes, of course, we have to put the model in evaluation mode. So that's one thing to keep in mind. With torch no grad, we saw it earlier. And what does the official documentation say? Let's see what happens. So ideally, our classes should be 0 because this is the MNIST data set. 1, 2, 3, 4. What about doing the softmax? We did not do any softmax here, so how are we getting the probabilities? Okay, ideally we should be doing a softmax. So taking a reference of episode 2 where we did softmax, the way I see it is once we have our outputs, then we need to run the softmax on the logit. So wherever we are doing the forward pass, which is here, prediction model X. So this prediction ideally should be giving us our logits. So what I'm going to do is softmax. This softmax should be, I think I can just define it here. And this can go here. Prediction probabilities. So instead of doing it on prediction, should do it on prediction probabilities. Okay, so instead of blindly following what ChatGPT had suggested, what I'm doing is I'm doing a little bit experimentation based on what I've learned so far. So let's see how it works. Okay, so I've got an error saying to tensor is not defined. I think it's an import error that I missed earlier. So from torch transforms, torch vision transforms. So this should be transforms to tensor based on this. So we will just make it like this. And then run it again. Okay, it works now. Okay, let's see, this works. Now, okay, our model is also created. Optimizer model. We created our network, but we did not put it to device. This thing we did not do. So we did not define our model object basically. Let's leave out the print statement. This goes here. Okay. Now this should work. Okay, works. Okay, so that works too. Epoch. So we have defined our epoch here. Should work. Okay, so it is training. So the model is training. Everything looks to be working fine so far. We will get back when the training is done. It's still going on for epoch 1. Okay, guys. So our training is complete. Um, you can see the training is complete. One thing to note here is loss has gone almost to 0, which sometimes means that model might be overfitting. But anyway, let's go ahead and see what happens. We are going to save our model. Model is saved. We are going to load our model. Okay, model is loaded. Now we are going to evaluate. So our thread here is the logits. Let's see. Okay, so Gemini told me that the problem was happening because the tensor by default accepts the first argument to be batch size, and what we were doing here is, because we were using just a single data, the batch size was being passed wrongfully. Okay, so it suggested to add a batch dimension, and then when I ran it, ran properly and gave the correct output. I want Okay, so I want to know more in detail of what this does. So let's ask Gemini to explain. Okay. Okay, so basically what this is doing is that it's specifying that the tensor that we have here of the image, its batch size is 1, because we intended to find it for a single data. So it's just specifying that in this particular tensor the batch size is 1, so it basically passes it, instead of passing it as channel height and width, it passes as 1 channel height and width. Okay, so this was great actually. Instead of blindly following what ChatGPT had suggested, we actually used our learnings from the previous 2 episodes, and we were successfully able to create a convolution neural network, and we also got the outputs. Let me just clear all outputs for once and test it for something else. Okay, this works perfectly fine. This is working perfectly fine. So yeah, we actually used our learnings and we created a convolution neural network. So this was great. Uh, in the next episode, we we will be inspecting graphs. So again, I don't really have much idea about what this is, but we'll see. So thank you all guys for watching and learning together with me. This series so far has been going great in my personal opinion, because I really got to learn, and I hope this will be helpful for you all also for learning. So yeah, thanks again and stay tuned.